Right now, a spacecraft is drifting through absolute darkness nearly 6 billion miles from Earth. It just woke up after sleeping for 321 days, and the signal confirming it was still alive took almost 9 hours travelling at the speed of light to reach us. That spacecraft is New Horizons, and it is moving through a region of the solar system that most people assume is empty. It is not. Beyond Neptune lies a vast frozen frontier filled with ancient icy debris, dwarf planets with glaciers and possible volcanoes, and dust that should not exist in the quantities instruments are detecting. The Kuiper Belt is not the clean boundary we were promised. It is darker, colder, stranger, and far less understood than any classroom diagram ever suggested. If you want to see why the space beyond the last giant planet is one of the most unsettling and least understood regions in our entire solar system, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. Every map of the solar system tells the same lie. The textbook version looks clean. 4 rocky planets near the Sun, then a belt of asteroids, then 4 giant planets, and finally Neptune, the last great world, orbiting at roughly 30 times the distance between Earth and the Sun. Beyond Neptune, the diagram fades to black. Maybe a dotted line hints at Pluto's orbit, maybe a faint label says Kuiper Belt. But the visual message is unmistakable. The interesting part of the solar system ends here. Neptune is the wall. Everything beyond it is footnote territory, a scattering of frozen debris too small and too far away to matter. That impression is wrong. Not slightly off, not a harmless simplification. It is fundamentally, structurally wrong, and it has shaped how generations of people think about the outer boundary of our planetary neighbourhood. Beyond Neptune lies not emptiness, but a vast, populated, gravitationally sculpted region, stretching billions of miles into the darkness. It contains thousands of known objects, and likely hundreds of thousands more that no telescope has ever seen. It holds dwarf planets with complex geology, ancient building blocks of the solar system preserved nearly unchanged for over 4 billion years, and a debris environment that recent instruments suggest is far more extensive than any model predicted. The Kuiper Belt is not a line at the edge of a diagram. It is a place, and it is immense. To understand what begins beyond Neptune, you first need to feel how far Neptune already is from everything familiar. Neptune orbits the Sun at an average distance of approximately 4.5 billion kilometers. That number is too large to process on its own, so consider what it means in terms of light. Sunlight, the fastest thing in the universe, takes about 8 minutes to travel from the Sun to Earth. To reach Neptune, that same light needs over 4 hours. If you sent a radio signal from Earth to a spacecraft at Neptune's distance, you would wait more than 8 hours for a round-trip reply. Every instruction, every course correction, every confirmation of survival crosses a gap so wide that real-time communication is impossible. At that distance, the Sun still dominates the sky. It remains the brightest object visible by a wide margin, but its warmth has largely vanished. The sunlight reaching Neptune is approximately 900 times weaker than what falls on Earth's surface. Noon on Neptune resembles something like deep twilight on Earth, enough to see by, but stripped of heat and intensity. Temperatures in Neptune's upper atmosphere plunge to around minus 214 degrees Celsius, making it one of the coldest planetary environments in the solar system. And Neptune is only the beginning of what lies beyond. For most of the 20th century, scientists had strong theoretical reasons to suspect that Neptune was not orbiting alone at the outer edge. The solar system formed from a vast rotating disk of gas and dust, and there was no physical reason for that disk to have simply stopped producing material at 30 astronomical units. In 1943, the Irish astronomer Kenneth Edgeworth proposed that a reservoir of small icy bodies should exist beyond Neptune, left over from the original planet-forming process. In 1951, the Dutch-American astronomer Gerard Kuiper made a similar argument, suggesting that the outer solar system should contain a belt of frozen debris too thinly spread to have coalesced into a full-size planet, but too massive to have simply disappeared. The region eventually took Kuiper's name, though Edgeworth arguably described it first. But knowing something should exist and actually finding it are different problems entirely. For decades, the only known object beyond Neptune was Pluto, discovered in 1930 by Clyde Tombaugh. Pluto was classified as the 9th planet for 76 years, and during that time it seemed like a lonely outpost, a single, small, icy world orbiting at the edge of everything. Astronomers searched for companions but found nothing. The Kuiper Belt remained a theoretical prediction without observational confirmation. The technology simply was not ready. Trans-Neptunian objects are small, typically ranging from a few kilometers to a few hundred kilometers across. They are dark, reflecting only a tiny fraction of the already feeble sunlight that reaches them, and they move with agonizing slowness against the background stars because objects at those distances take centuries to complete a single orbit around the Sun. Detecting something that dim and that slow requires large telescopes, sensitive digital cameras, and painstaking comparison of images taken hours or days apart. None of that was available at the precision needed until the late 20th century. The breakthrough came in 1992. David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, discovered a faint object designated 1992 QB1. It was small, roughly 160 kilometers across, orbiting the Sun well beyond Neptune at a distance of about 44 astronomical units. It was not Pluto. It was not a comet in any traditional sense. It was exactly the kind of cold, ancient, icy body that Edgeworth and Kuiper had predicted a leftover from the formation of the solar system, sitting quietly in the darkness where it had been for billions of years. That single discovery cracked open the outer solar system. Within a few years, dozens more objects appeared, then hundreds, then thousands. Telescopes around the world turned toward the ecliptic plane beyond Neptune and found object after object, each one a frozen relic orbiting in the dim outer reaches. The theoretical Kuiper Belt became an observational reality, and it was far richer and more structured than a simple band of scattered debris. As of 2025, over 5,000 trans-Neptunian objects have been catalogued, and the actual population is estimated to be vastly larger. Models suggest the Kuiper Belt contains roughly 100,000 objects larger than 100 kilometers in diameter, and potentially billions of smaller bodies ranging down to the size of boulders and pebbles. The total mass of the belt is modest. Current estimates place it at a small fraction of Earth's mass, perhaps a few hundredths, but it is spread across an enormous volume of space. The Kuiper Belt is not a thin ring. It is a broad, thick, donut-shaped region stretching from roughly 30 astronomical units near Neptune's orbit outward to at least 50 astronomical units, and possibly much farther. That shape and extent are not accidental. Neptune did not just happen to orbit at the inner edge of a debris field. Neptune sculpted the Kuiper Belt. Its gravity is the dominant force shaping the orbits, populations, and structure of everything in this region, and understanding that gravitational influence is the key to understanding why the space beyond Neptune looks the way it does. When the solar system was young, Neptune did not sit where it orbits today. The leading model of early solar system evolution, known as the Nice model after the city in France where it was developed, proposes that Neptune formed closer to the Sun and migrated outward over hundreds of millions of years. As Neptune moved through the primordial disk of icy debris, its gravity interacted with countless small bodies. Some were flung inward, toward the Sun, becoming the source population of short-period comets. Some were scattered outward onto wild, elongated orbits that carry them hundreds of astronomical units from the Sun before swinging back. And some were captured into gravitational resonances, stable orbital patterns, where the small body's orbital period is locked into a precise ratio with Neptune's. These resonances are not abstract mathematical curiosities. They are physical traps that organize the Kuiper Belt into distinct populations. The most famous resonance is the 2-to-3 resonance, where an object completes exactly 2 orbits around the Sun for every 3 orbits Neptune completes. Pluto sits in this resonance. So do thousands of other objects, collectively known as Plutinos. Their orbits are not identical to Pluto's, but they share the same gravitational relationship with Neptune, protecting them from close encounters even though their paths cross Neptune's orbit. Without this resonance, Pluto would have been ejected from the solar system or destroyed by a collision with Neptune billions of years ago. Instead, The resonance acts as a shield, keeping Pluto and its companions safe in a gravitational pocket that Neptune itself created during its ancient outward migration. Other resonances exist at different orbital ratios, the 1:2, the 3:5, the 4:7, each capturing a population and locking it into a specific orbital pattern. Together, these resonant populations form the skeletal framework of the Kuiper Belt's observed structure. Between the resonances lies the classical Kuiper Belt, sometimes called the cold classical belt, because its members have low orbital inclinations and relatively circular orbits. These are objects that appear to have formed roughly where they orbit today, undisturbed by Neptune's migration. Their orbits are calm, their inclinations are small, and their surfaces tend to be unusually red, a colour signature associated with ancient organic compounds that have been slowly processed by cosmic radiation over billions of years. The cold classical belt is thought to be the most primordial population in the Kuiper Belt, a sample of material that has remained largely undisturbed since the solar system's formation roughly 4.5 billion years ago. Arrokoth, the snowman-shaped object visited by New Horizons in 2019, is a cold classical Kuiper Belt object, and its remarkably pristine condition supports the idea that this population has been sitting in cold storage for longer than Earth has existed. In contrast, the scattered disk is a far more chaotic population. Scattered disk objects have orbits that are highly elongated and steeply inclined, carrying them from near Neptune's orbit out to hundreds or even thousands of astronomical units before swinging back. These objects were not gently placed on their current paths. They were hurled there by gravitational encounters with Neptune, flung outward like stones from a slingshot. Their orbits are unstable over long timescales, and many scattered disk objects will eventually be perturbed again, either ejected from the solar system entirely or pushed inward to become centaurs, the transitional objects that orbit between the giant planets before eventually becoming short-period comets. Eris, the most massive known dwarf planet, is a scattered disk object. It orbits the Sun on a path that takes it from about 38 astronomical units at its closest approach to nearly 98 astronomical units at its most distant point. A single orbit takes Eris roughly 558 years. At its current distance of approximately 96 astronomical units, Eris is one of the most remote known objects in the solar system, so far away that sunlight takes over 13 hours to reach it. Eris is slightly more massive than Pluto, though Pluto is slightly larger by volume, a difference that contributed directly to the crisis in planetary classification. The discovery of Eris in 2005 forced the astronomical community to confront a question it had been avoiding. If Pluto was a planet, then Eris had to be one too, and so did every comparable body waiting to be found. The International Astronomical Union resolved the dilemma in 2006 by creating the dwarf planet category and demoting Pluto into it. The debate over that decision continues to this day, but the scientific reality behind it is not in question. Pluto is not alone. It is one member of a large and diverse population. The dwarf planet category now includes several trans-Neptunian objects, each one a world in its own right. Pluto, with its nitrogen glaciers and thin atmosphere. Eris, dense and distant, with a moon called Dysnomia. Haumea, the egg-shaped body spinning so rapidly that it has been stretched into an ellipsoid, with a collisional family of fragments and a ring system discovered through stellar occultation observations in 2017. Makemake, a methane-rich world about two-thirds the size of Pluto, orbiting at roughly 45 astronomical units and taking approximately 310 years to complete a single trip around the Sun. Gonggong, a reddish dwarf planet in the scattered disk with a moon called Shongliu. And those are only the confirmed dwarf planets. Dozens of additional trans-Neptunian objects are large enough that they probably qualify, but have not yet been formally classified. The outer solar system went from containing exactly one known body beyond Neptune-Pluto to containing thousands, all within a single human generation. This explosion of discovery revealed something else. The Kuiper Belt is not a uniform slab of debris. It has internal structure, population boundaries, density variations and gaps. Some of these features are well explained by Neptune's gravitational influence. The resonant populations, the dynamically hot and cold classical populations, the inner edge shaped by Neptune's orbit, All of these follow from known physics and well-tested models of planetary migration. But other features remain puzzling. The outer edge of the classical Kuiper Belt appears to drop off sharply near 50 astronomical units. Object density declines steeply, and beyond 50 astronomical units, the known population thins dramatically. For years, this was interpreted as the genuine outer boundary, the point where the original disk ran out of material, or where some dynamical process cleared the region. That interpretation was clean, satisfying, and increasingly difficult to defend. The problem started with the dust. The New Horizons spacecraft carries an instrument called the Venetia-Burney Student Dust Counter, a detector designed to measure impacts from microscopic interplanetary dust particles along the spacecraft's entire flight path. Dust in the outer solar system is produced primarily by collisions between Kuiper Belt objects and by the steady bombardment of those objects by interstellar dust grains streaming into the solar system from the surrounding galaxy. Models predicted that the dust density should peak somewhere around 40 astronomical units, near the heart of the classical Kuiper Belt, and then decline rapidly as the spacecraft moved past the belt's supposed outer edge. The dust counter told a different story. As New Horizons passed 40 astronomical units, the dust density did not decline. It remained elevated. As the spacecraft pushed through 45, 50, 55 astronomical units, the dust kept coming at levels 2 to 3 times higher than models predicted. A study published in the astrophysical journal Letters in early 2024 reported these unexpectedly high fluxes through 55 astronomical units, with no sign of the expected drop-off. A follow-up analysis published in 2025 examined whether the excess could be explained by the behavior of the dust grains themselves. Icy particles being pushed outward by solar radiation, pressure, or volatile coatings being stripped by ultraviolet light, altering the grain's response to radiation forces. Both effects likely contribute. But a third possibility loomed larger and harder to dismiss. The population of parent bodies producing this dust may extend far beyond the region where ground-based surveys have found Kuiper Belt objects. The dust is a signal. It is telling us that something is generating debris in a region that was supposed to be nearly empty. Supporting evidence came from a completely independent direction. The New Horizons mission team, working with the Subaru telescope in Hawaii, conducted deep surveys along the spacecraft's trajectory using the telescope's ultra-wide-field camera. In 2024, the team published results in the Planetary Science Journal reporting the detection of candidate trans-Neptunian objects at distances stretching out toward 90 astronomical units, nearly twice the supposed outer edge of the classical belt. The sample was small. The orbits of these candidates were not fully determined, but the detections were consistent with a population of distant bodies that existing surveys had missed entirely. New Horizons principal investigator Alan Stern described these findings as evidence for a possible second Kuiper Belt or an extended outer population. That phrase requires careful handling. A second Kuiper Belt is not a confirmed discovery. It is a candidate interpretation of limited data. The objects detected by the Subaru survey could belong to the scattered disk, or they could be outliers of the classical population on unusual orbits. Determining their true nature requires tracking them over multiple years to pin down their orbital paths, and that work is ongoing. But the combination of unexpectedly high dust levels and candidate distant objects paints a consistent picture. The outer solar system does not end where the textbooks say it does. The timing of this realization matters. For decades, the sharp outer edge of the Kuiper Belt, near 50 astronomical units, was treated as a boundary condition, a constraint that models of planet formation used to set the size of the original solar nebula. Theories of Neptune's migration were tuned to reproduce it. The edge was treated as a fact of nature. Now, that fact is under revision, and the consequences ripple outward through every model built on top of it. The Kuiper Belt is not just a collection of icy leftovers. It is a fossil record. The objects in the belt, their sizes, their orbits, their compositions, their spatial distribution encode information about conditions that existed when the solar system was forming over 4.5 billion years ago. The architecture of the belt reveals where the giant planets were, how they moved, how violently they interacted with the debris around them, and how much material was available in the outer disk. If the belt is larger than we thought, If significant populations of objects exist beyond 50 astronomical units in a region we assumed was cleared, that changes the initial conditions. It means the solar nebula may have been more extensive than current models assume. It means Neptune's influence may have shaped a larger volume of space than previously calculated. And it means that the transition from the organized planetary solar system into the chaotic outer frontier is not a clean line, but a gradual, poorly mapped fade. Consider the scale involved. If you compressed the entire solar system into a model where Earth orbited 1 meter from the Sun, Neptune would sit 30 meters out, and the outer boundary of the classical Kuiper Belt would be 50 meters from the Sun, a sphere of space large enough to contain a generous backyard. But the scattered disk objects range far beyond that boundary. Sedna, one of the most distant known objects, has an orbit that carries it from about 76 astronomical units at its closest approach to roughly 937 astronomical units at its farthest point. On the same scale model, Sedna's most distant position would be nearly a kilometre from the Sun, and the hypothesized Oort cloud, the vast spherical reservoir of icy bodies from which long-period comets are thought to originate, may extend to 50,000 or even 100,000 astronomical units. On our model, the Oort cloud's outer edge would reach 50 to 100 kilometers in every direction. The Kuiper Belt is not the outer edge of the solar system. It is the beginning of the outer solar system. Neptune's role in all of this is paradoxical. It is simultaneously the guardian and the destroyer of the Kuiper Belt. Its gravitational resonances protect populations like the Plutinos, locking them into stable orbits that have persisted for billions of years. But Neptune's gravity also destabilizes objects that are not safely tucked into resonances. Any Kuiper Belt object that drifts too close to Neptune risks a gravitational interaction that can send it careening inward toward the Sun, outward into the scattered disk, or out of the solar system entirely. Over the age of the solar system, Neptune has steadily eroded the Kuiper Belt's population, scattering objects away and thinning the debris field. The belt we observe today is a remnant, a fraction of the original population that survived Neptune's gravitational sorting over 4 billion years. This erosion has not stopped. Neptune continues to perturb objects near its orbit. Kuiper Belt objects continue to be scattered, some falling inward to become centaurs and eventually short-period comets, others being flung into the scattered disk or beyond. The Kuiper Belt is not a static structure frozen in place since the solar system's youth. It is a slowly evolving population being gradually depleted by the gravitational influence of the planet next door. At the same time, Neptune's influence weakens with distance. Objects beyond roughly 50 astronomical units are far enough from Neptune that its gravitational perturbations become feeble. This is one reason the sharp edge of the classical belt near 50 astronomical units was so puzzling. If Neptune's gravity cannot easily reach that far, something else must have truncated the region. Possible explanations include the natural outer limit of the original solar nebula, a passing star that stripped material from the outer disk early in the solar system's history, or the gravitational influence of an undiscovered massive body. None of these explanations is definitively confirmed. Each one carries implications that ripple through the rest of planetary science. What is confirmed is that the known Kuiper Belt, even without any extensions or second belts, is already a staggeringly complex region. It contains multiple dynamically distinct populations, shaped by billions of years of gravitational interaction with Neptune. It hosts at least 5 recognized dwarf planets, and probably dozens more awaiting formal classification. Its members range from tiny fragments to worlds over 2,000 kilometers across. Their surfaces display colors spanning from neutral grey to deep red, indicating a wide range of compositions and radiation processing histories. Some are rich in water ice, some are coated in methane and nitrogen ices, some bear the dark reddish residue of organic compounds irradiated by cosmic rays over timescales longer than the age of complex life on Earth. They are not all the same, they are not all simple, and they are emphatically not just frozen rocks drifting through nothingness. Yet for all of this, the most unsettling fact about the Kuiper Belt is how little of it we have actually seen. Current surveys are sensitive enough to detect objects roughly 100 to 200 kilometers across at distances of 40 to 50 astronomical units. Anything smaller, anything farther, or anything on an orbit that keeps it away from the ecliptic plane where most surveys concentrate remains invisible. The 5,000 known trans-Neptunian objects represent the bright, nearby, easy-to-find fraction of a population that almost certainly numbers in the hundreds of thousands at minimum. The Kuiper Belt we have mapped is a sketch, not a portrait. Every new telescope that looks deeper finds more objects, more structure, more evidence that the outer solar system is richer and more extended than the previous generation of instruments could reveal. The Vera Rubin Observatory, which officially began its legacy survey of space and time in July of 2026, is expected to transform this picture entirely. Equipped with the largest digital camera ever built for astronomical surveying, Rubin will scan the southern sky repeatedly for a decade, imaging the same patches with enough depth and cadence to catch the slow-moving signatures of distant trans-Neptunian objects that every previous survey has missed. Projections suggest the survey will discover approximately 35,000 new Kuiper Belt objects within its first few years, increasing the known population nearly tenfold. That flood of data will reveal whether the outer edge of the belt is real, or whether populations extend smoothly outward into regions no previous instrument could reach. It will test models of Neptune's migration by mapping the orbital distribution of belt objects with unprecedented statistical power, and it will search for the faint gravitational fingerprints of any massive unseen body lurking in the outer darkness, a question that has haunted planetary science for over a decade and remains unanswered. But Rubin's full results will take years to deliver. In the meantime, the only spacecraft actively exploring the Kuiper Belt is New Horizons, currently drifting through the region at approximately 64 astronomical units from the Sun. Its dust counter keeps recording impacts, its plasma instruments keep measuring the solar wind, its ultraviolet spectrograph keeps mapping hydrogen in the outer heliosphere, and the dust keeps coming, in quantities that no model fully explains, from a region that was supposed to be empty by now. The Kuiper Belt was supposed to fade away neatly around 50 astronomical units. The data say otherwise. Something unexpected inhabits the space beyond the known belt: more dust, candidate distant objects, and a structural complexity that existing models cannot cleanly reproduce. The outer solar system has not ended. It has only gotten harder to see, and what the few instruments capable of looking out there have found icy worlds with active geology, primordial relics with surfaces unchanged since the birth of the planets, and a debris field that refuses to thin out on schedule turns out to be stranger and more scientifically unsettled than anyone who drew those clean textbook diagrams ever anticipated. Nobody expected Pluto to have a heartbeat. Before New Horizons arrived in July of 2015, the best image of Pluto was a handful of blurred pixels from the Hubble Space Telescope. Scientists could see patches of light and dark material and infer from spectroscopy that nitrogen, methane, and carbon monoxide ices were present. They knew Pluto had a thin atmosphere and a large moon called Chiron, but the details, the geology, the texture, the actual landscape were completely unknown. Pluto was a smudge. It had been a smudge for 85 years, ever since Clyde Tombaugh first spotted it as a faint dot drifting slowly across photographic plates in 1930. The prevailing expectation was modest. Most scientists anticipated a geologically dead ice ball, cratered and inert, a frozen fossil from the outer solar system's formation that would be interesting but ultimately simple. New Horizons shattered that expectation within hours of its closest approach. The first high-resolution images revealed a feature so unexpected that mission scientists initially doubted their instruments. Sprawled across Pluto's equatorial region was an enormous heart-shaped deposit of bright ice, informally named Tombaugh Regio after Pluto's discoverer. The left lobe of this heart turned out to be one of the most remarkable geological features ever discovered in the solar system. Sputnik Planitia is a basin roughly 1,000 kilometers across, comparable in area to the state of Texas, filled to a depth of several kilometers with solid nitrogen ice. Its surface is almost perfectly smooth. There are virtually no impact craters, which in planetary science means one thing: the surface is young. On a world 4.5 billion years old, a surface without craters is a surface that has been erased and rebuilt over and over by some active process. That process turned out to be convection. The nitrogen ice filling Sputnik Planitia is not sitting still. It is slowly churning. Thermal energy from Pluto's interior, modest by any terrestrial standard, but sufficient to mobilize nitrogen ice at temperatures near 35 to 40 Kelvin, drives sluggish, convective overturn in the ice. Sheet. Warmer nitrogen rises from below, spreads across the surface, cools, and sinks back down at the margins. This circulation creates a pattern of polygonal cells visible from orbit, each one roughly 20 to 40 kilometers across, with their boundaries marked by darker troughs where ice descends. The entire surface of Sputnik Planitia refreshes itself on a timescale of roughly 500,000 years. In geological terms, that is extraordinarily fast. It means that any crater formed by an impacting object is eventually swallowed, subducted into the churning ice, and erased from the record. Nitrogen ice at these temperatures behaves unlike anything in ordinary human experience. At 40 Kelvin, roughly minus 233 degrees Celsius, nitrogen ice is a solid, but it is a geologically soft solid. It deforms and flows under its own weight, much as glacial ice flows on Earth, though far more slowly and under very different conditions. This softness allows nitrogen to act as a geological agent, filling basins, flowing through valleys, and transporting material across hundreds of kilometers. Along the eastern edge of Sputnik Planitia, New Horizons imaged nitrogen ice glaciers actively flowing into the basin from the surrounding highlands. Dark flow lines streaked through narrow valleys, descending from elevated terrain and spreading into fan-shaped deposits at the basin margin. These glaciers are not relics. They are moving now, driven by the same volatile cycle that governs Sputnik Planitia's convection. Climate models show that nitrogen ice sublimes from the sun-facing portions of the basin, enters Pluto's atmosphere as gas, travels through the thin air, and recondenses on colder surfaces elsewhere. Over one Pluto day, roughly 6.5 Earth days, approximately a millimeter of nitrogen ice transfers from one part of the basin to another. Integrated over millions of years, this produces kilometers of ice transport. Glaciers flow into the basin under gravity while sublimation and recondensation redistribute ice across the broader landscape. Pluto has a nitrogen cycle, analogous in structural terms to Earth's water cycle, operating at temperatures where water itself is a rigid, stone-like material. The mountains surrounding Sputnik Planitia delivered another shock. Pluto's mountains are made of water ice. At 40 Kelvin, water ice has the mechanical strength of rock. It does not flow, does not deform, and does not erode under the feeble forces available on Pluto's surface. The mountains near Sputnik Planitia, including ranges informally named after Edmund Hillary and Tenzing Norgay, rise 1 to 3 kilometers above the surrounding terrain. Built from blocks of water ice that appear to have been broken and pushed around by geological forces, and their peaks are white, not with water frost, but with methane frost. Bright methane ice coats the highest elevations, creating a visual effect eerily similar to snow-capped mountains on Earth. But the mechanism is entirely different. On Earth, temperature decreases with altitude, causing water vapor to condense on mountaintops. On Pluto, methane frost accumulates at high elevations because of a quirk in the atmospheric circulation. The methane concentration in the atmosphere increases with altitude, and at sufficient height, the air becomes cold and methane-rich enough for frost to condense directly onto the surface. The result looks familiar but operates through alien physics. East of Tombau Regio, the terrain becomes stranger still. A region called Tartarus Dorsa is covered in formations unlike anything else in the solar system, towering blades of methane ice, each one hundreds of meters tall, standing in dense parallel rows that extend across hundreds of kilometers of terrain. These features resemble terrestrial penitentes, the spiky ice formations found at high altitudes in the Andes, but scaled up enormously. On Earth, penitentes grow to a meter or two at most. On Pluto, the same basic process, differential sublimation driven by sunlight hitting an icy surface at steep angles, has had millions of years and an uninterrupted supply of methane ice to work with. The result is a landscape of knife-edged ridges separated by deep troughs, covering an area so vast and so geometrically regular that it resembles a frozen forest of ice blades viewed from above. The bladed terrain tells scientists that methane ice has been deposited, sculpted, and reworked on Pluto's surface over extended timescales. confirming that the volatile cycle does not merely redistribute nitrogen within Sputnik Planitia, but operates across the entire world, moving methane between hemispheres and between highlands and lowlands as Pluto's seasons shift over its 248-year orbit. Then there were the volcanoes. South of Sputnik Planitia, New Horizons imaged a region of enormous mounds with hummocky, undulating flanks, terrain unlike anything previously seen in the solar system. The largest of these features, Wright Mons and Picard Mons, rise several kilometers above the surrounding landscape and span 100 to 200 kilometers across. Their morphology, broad, domed structures with summit depressions, strongly resembles volcanic constructs, but these are not lava volcanoes. They are cryovolcanoes, built from the eruption of icy material from Pluto's interior. A study published in Nature Communications in 2022 by Kelsey Singer and colleagues on the New Horizons team concluded that cryovolcanic processes resurfaced this entire region, requiring multiple eruption sites and an enormous volume of erupted material, more than 10,000 cubic kilometers to create the observed terrain. The lack of impact craters on these features indicates that the most recent cryovolcanic activity occurred within the past 1 to 2 billion years, and possibly much more recently. Elsewhere on Pluto, trench-like features called graben, and even a putative caldera near Kiladze crater, show spectral signatures of water ice with ammoniated compounds. Ammonia is thought to be destroyed relatively quickly on Pluto's surface by radiation, so its detection implies that the eruptions exposing it are geologically recent, less than 1 billion years old. The implication is stark. Pluto has enough internal heat to drive volcanic eruptions on a world smaller than Earth's moon in diameter, orbiting nearly 40 times farther from the Sun than Earth, where surface temperatures make liquid nitrogen a reasonable geological material. The interior has somehow retained enough warmth over 4.5 billion years to mobilize icy mixtures and push them to the surface. Where that heat comes from is not fully settled. Radioactive decay in Pluto's rocky core is the most likely primary source, but whether Pluto also retains heat from its formation or from tidal interactions with Chiron remains an open question. A 2026 paper in Nature Communications titled Pluto, Dazzling, Dynamic, and So Not Dead, summarized the state of knowledge plainly. Pluto exhibits active geology and a dynamic atmosphere. It is not a frozen wasteland, and its authors noted that Pluto should be considered a preview of what to expect from other large trans-Neptunian objects, not an exception. Even Pluto's atmosphere, thin as it is roughly 100,000th the pressure of Earth, supports active weather phenomena. Haze layers extend over 200 kilometers above the surface, built from organic particles produced by ultraviolet processing of methane and nitrogen gases. These haze particles settle onto the surface over time, contributing to the reddish-brown coloring visible across much of Pluto's terrain. Winds on the order of 1 meter per second leave dark streaks on the surface, and the entire atmosphere is impermanent. Pluto's surface pressure varies dramatically over its 248-year orbit, as the distance to the Sun changes and nitrogen ice sublimates or recondenses in response. Models suggest the atmosphere is currently near its peak pressure and will undergo a sharp decline within the next decade or so as Pluto's northern hemisphere shifts from summer into winter. A world with a collapsing atmosphere that will rebuild itself centuries later is not a dead world. Charon, Pluto's largest moon, added its own set of surprises that deepened the story. At roughly 1,200 kilometers in diameter, about half the size of Pluto-Chiron, is large enough that the Pluto-Chiron system is sometimes called a double dwarf planet. The two bodies orbit a common center of gravity, located in the space between them, locked in a mutual tidal embrace where the same face of Chiron always points toward Pluto. Scientists expected Chiron to be simpler than Pluto, a smaller, colder body with fewer resources for geological activity. Instead, New Horizons revealed a world that had been cracked open from the inside. Chiron's most dramatic feature is a system of enormous canyons and troughs stretching across its equatorial and southern regions. Serenity Chasma, the largest, runs for over 1,000 kilometers, a rift valley deeper than the Grand Canyon slicing across a world barely a third the diameter of our moon. Argo Chasma, in the southern hemisphere, appears to reach depths of 9 kilometers based on shadow measurements, making it one of the deepest known canyons in the solar system relative to the size of the body it crosses. These are not impact features. They are tectonic fractures, cracks formed when Charon's crust was pulled apart by forces originating from within. The most likely explanation is ice expansion. If Charon once harbored a subsurface ocean of liquid water that subsequently froze, the volume increase as water turned to ice, roughly 9% expansion, would have generated enormous stress on the overlying crust. The surface would have cracked, producing exactly the kind of extensional tectonics visible in the canyon systems. The canyons are the scars of a moon that froze from the inside out, its own solidifying ocean splitting its face open. Whether any liquid remains today is unknown. The evidence does not require a present-day ocean, only a past one, but the timing is ambiguous. If the freezing is still ongoing, pockets of liquid could persist at depth, insulated by the ice shell above. The northern polar region tells a different story. Chiron's north pole is covered by a dark reddish cap, informally named Mordor Macula, visually striking against the moon's otherwise grey terrain. This cap is thought to be composed of organic compounds called tholins, complex reddish-brown molecules built from simpler precursors like methane and nitrogen. The leading hypothesis is that methane gas escaping from Pluto's atmosphere drifts outward, some of it reaching Chiron's cold polar regions, where ultraviolet radiation from the distant sun and energetic particles from the solar wind process it into heavier organic molecules. These tholins accumulate on the surface over millions of years, painting the pole with a veneer of irradiated organic sludge. Chiron is not generating these compounds internally. It is catching them from Pluto, a chemical conversation between two tidally locked worlds separated by roughly 19,000 kilometers of empty space. If Pluto demonstrated that large trans-Neptunian objects can be geologically complex, Arrokoth demonstrated that even tiny ones can be scientifically profound. New Horizons flew past Arrokoth, formerly designated 2014 MU-69, on January 1st, 2019, at a distance of roughly 3,500 kilometers. Horizon. Arrokoth is a cold classical Kuiper Belt object, one of the primordial inhabitants of the belt that appears to have formed close to where it currently orbits and remained undisturbed for billions of years. It is about 36 kilometers long. It weighs essentially nothing by planetary standards, and its shape is one of the most informative in the solar system. Arrokoth is a contact binary. It consists of two flattened lobes joined at a narrow neck, resembling a snowman that has been gently pressed from both sides. The larger lobe, named Wenu, is roughly twice the volume of the smaller lobe, Weo. Both lobes are remarkably smooth, with very few impact craters, a surface that has accumulated almost no hits over 4.5 billion years of exposure. That emptiness carries deep implications for the Kuiper Belt's collision history. But what matters first is what the smoothness reveals about formation. This is not a body that was battered into its current shape. It is a body that was built gently and left alone. The shape itself is a forensic record. Detailed analysis of Arrokoth's structure, the alignment of its lobes, the orientation of its spin axis, the smoothness of its surface indicates that the two lobes formed near each other within a localized cloud of material that collapsed under its own gravity. They became a gravitationally bound pair, orbiting one another, gradually losing angular momentum through gas drag or tidal interactions, and eventually drifting together in a gentle merger at speeds of only a few meters per second. The impact was so soft that neither lobe was significantly deformed or damaged. A 2026 study using numerical simulations confirmed that contact binaries like Arrokoth can form directly through the gravitational collapse of pebble clouds in the early solar nebula, a process called streaming instability. This is profoundly different from the older model of planetesimal formation, which imagined small bodies being built up gradually through high-speed collisions. Arrokoth's shape is evidence that at least some planetesimals were born gently, assembling themselves from small particles that clumped together under gravity in a calm environment. Arrokoth's surface composition added further clues. The LASAR infrared spectrometer on New Horizons detected clear signatures of methanol on the surface, but no definitive evidence for water ice. The surface is uniformly reddish, consistent with organic compounds processed by billions of years of cosmic ray bombardment. These are not materials that formed under violent conditions. They are the chemical fingerprints of slow, patient radiation processing in cold, quiet space. Arrokoth is a time capsule, a fragment of the original solar nebula preserved in the freezer of the outer solar system, for longer than complex life has existed on Earth. But the revelations from the trans-Neptunian region have not come only from spacecraft. The James Webb Space Telescope, operating from its orbit near the Sun-Earth second Lagrange point, roughly 1.5 million kilometers from Earth, has turned its infrared instruments toward the outer solar system and uncovered chemistry that was invisible to every previous observatory. Makemake, the second largest classical Kuiper Belt object after Pluto, was long considered one of the more enigmatic dwarf planets. It orbits at roughly 45 astronomical units and takes approximately 310 years to circle the Sun. Its surface was known to be covered in methane and ethane ices, but the details of its composition and any atmospheric activity remained uncertain. In 2025, a team using the James Webb Space Telescope reported the detection of methane gas around Makemake, making it only the second trans-Neptunian object after Pluto where atmospheric gas has been confirmed. The methane was identified through a technique called solar-excited fluorescence, in which sunlight is absorbed and re-emitted by methane molecules above the surface. The detection suggests that Makemake possesses either an extremely tenuous atmosphere in equilibrium with its surface ices, or an exosphere, a region where individual gas molecules escape the surface and follow ballistic trajectories before falling back or being lost to space. Even more striking was a separate James Webb discovery. In 2024, a team led by Kiss reported a prominent mid-infrared excess from Makemake that could not be explained by passive thermal emission from a uniformly cold surface. The excess suggested the presence of localized warm spots, small areas significantly hotter than the surrounding terrain. One interpretation is ongoing cryovolcanic activity, similar in concept to the geysers on Saturn's moon Enceladus, though likely operating through different mechanisms. If confirmed, this would mean that Makemake, a world roughly two-thirds the size of Pluto orbiting far from the Sun in temperatures around 40 Kelvin, is actively venting material from its interior. The finding is not yet definitive. The warm spots could have alternative explanations, including unusual surface thermal properties or compositional heterogeneity. But the data are consistent with a geologically active world, and follow-up observations are underway. Eris, the most massive known dwarf planet, yielded its own chemical surprise. Despite orbiting at a current distance of approximately 96 astronomical units so far from the Sun, that sunlight takes over 13 hours to arrive. Eris and its moon Dysnomia have been targets of James Webb, observations that measured the D to H ratio in the methane ice on its surface. The D to H ratio is a chemical fingerprint. Different sources of methane, primordial methane, accreted from the solar nebula, methane produced by geological processes in the interior. Methane delivered by cometary impacts carry different ratios of deuterium to hydrogen. The measurements published in 2024 by Christopher Glein and colleagues found moderate D to H ratios on both Eris and Makemake, inconsistent with purely primordial origins. The results suggest that hydrothermal or metamorphic processes in the interiors of these worlds have chemically processed the methane, producing new methane through reactions between water and rock at elevated temperatures deep below the surface. This means that the methane on these distant worlds is not simply ancient frost left over from the formation of the solar system. At least some of it was manufactured inside the dwarf planets themselves, through chemistry that requires liquid water interacting with rocky minerals at temperatures far above what exists on the surface. If this interpretation is correct, it implies that Eris and Makemake have or once had warm interiors warm enough for water to remain liquid at depth, warm enough for rock-water chemistry to operate, warm enough to drive geological processes that replenish surface volatiles from below. On worlds this small, this cold, and this far from the Sun, that is a remarkable claim. But the chemical evidence supports it, and no alternative explanation has cleanly replaced it. The picture broadens further. James Webb observations of Sedna, Gong, and Kwa-Or, published in 2024, revealed volatile ices and organic materials on all three objects. with compositions suggesting that surface volatiles are being replenished rather than simply sitting unchanged since formation. Quaoar, a trans-Neptunian object roughly 1,100 kilometers in diameter, possesses a ring system discovered through stellar occultation. In 2023, a dense ring orbiting outside the Roche limit, the distance within which tidal forces should tear a ring apart. The ring's survival challenges existing models of ring dynamics and raises questions about whether it is being actively fed by material from Quaoar's surface. Haumea, the rapidly spinning dwarf planet whose elongated shape results from an ancient collision that shattered a larger body and created a family of fragments, also hosts a ring system detected by stellar occultation in 2017. Haumea spins so fast, completing a rotation in under 4 hours, that it has been stretched into a shape resembling a flattened rugby ball. Its surface is dominated by crystalline water ice, which is unusual because cosmic radiation should have converted it to amorphous ice over billions of years. The presence of crystalline ice suggests either recent resurfacing or ongoing energy input that recrystallizes the ice. Haumea's 2 moons, Hi'iaka and Namaka, orbit in complex patterns that continue to be refined by observations. The entire system, dwarf planet, moons, ring, collisional family represents a level of dynamical complexity that would have seemed implausible for an object this far from the Sun before it was actually observed. What makes all of this even more striking is that the scientific community received its first warning decades before New Horizons reached Pluto. In 1989, Voyager 2 flew past Neptune and turned its cameras toward Triton, Neptune's largest moon. Triton orbits Neptune backward in the opposite direction to the planet's rotation, which is powerful evidence that it did not form alongside Neptune, but was instead gravitationally captured from a heliocentric orbit. Most planetary scientists now consider Triton to be a captured Kuiper Belt object, a trans-Neptunian world that wandered too close to Neptune and was pulled into orbit around it. If that is correct, Triton is the only large trans-Neptunian body besides Pluto that a spacecraft has studied up close. What Voyager 2 found was astonishing for its time. Triton's surface was geologically young, with very few impact craters. Its southern hemisphere was covered in a pinkish frost of nitrogen and methane ices, and most remarkably, the spacecraft observed active geysers, dark plumes of nitrogen gas, and entrained dust erupting from the surface to heights of roughly 8 kilometers before being swept sideways by thin upper atmosphere winds into long, horizontal streaks. They were active eruptions captured in real time by a passing spacecraft on a world where surface temperatures measured approximately -235 degrees Celsius. Triton demonstrated in 1989 that geological activity could persist on an icy body far from the Sun, in conditions cold enough to freeze nitrogen solid. The lesson should have prepared the community for what New Horizons would find at Pluto 26 years later. In many ways, it did. But the sheer breadth and variety of active processes on Pluto, convection, glaciation, cryovolcanism, atmospheric cycling, bladed terrain formation, exceeded even the expectations that Triton had set. Triton remains a tantalizing target. No spacecraft has returned since Voyager 2, and the side of Triton not photographed during the brief flyby remains unknown terrain. Its interior structure, potential subsurface ocean, and geyser mechanisms are all unresolved. If Triton is indeed a captured Kuiper Belt object, studying it in detail would provide a window into what a large trans-Neptunian world looks like when it has been subjected to billions of years of tidal heating and gravitational interaction with a giant planet, a very different, evolutionary path from the cold isolation that Pluto and the other dwarf planets have experienced. Each new observation reinforces the same conclusion. The trans-Neptunian region is not a freezer full of inert leftovers. It is a gallery of worlds with active surfaces, complex interiors, and chemical processes that are still operating billions of years after formation. Pluto has glaciers and volcanoes, and an atmosphere that rises and collapses over the course of its orbit. Its bladed terrain testifies to volatile cycling on continental scales. Charon carries the fracture scars of a frozen internal ocean and wears a cap of organic material delivered from its partner world. Arrokoth preserves the gentlest moments of planetary formation in its undamaged shape. Makemake vents methane gas and may host warm spots that hint at geological activity. Eris and Makemake manufacture methane through interior chemistry that requires liquid water. Kwa and Haumea wear rings that defy simple explanations. Sedna and Gongong display volatile inventories that look replenished rather than static. And Triton, likely a captured member of this same population, showed active geysers erupting from its frozen surface nearly 4 decades ago. The old assumption that distance from the Sun equals geological death has been thoroughly overturned. These worlds are cold beyond any terrestrial comparison. Their surfaces sit at temperatures where nitrogen is a solid, methane is a rock, and water ice has the structural strength of granite. And yet they move, they flow, they erupt, they cycle gases through atmospheres thinner than a laboratory vacuum. They produce organic compounds and harbour chemistry that points to warm, wet interiors hidden beneath crusts of ice harder than stone. The question is no longer whether these frozen worlds are active. The evidence on that point is overwhelming and continues to accumulate with every new telescope observation and every new analysis of existing spacecraft data. The question now is, how? How does a world the size of Pluto, receiving roughly 1/900th the sunlight that Earth enjoys, maintain enough internal energy to drive cryovolcanism for billions of years? How does a body the size of Makemake sustain methane gas above its surface and possibly vent warm material into space? How do objects this small avoid cooling into complete inertness over the age of the solar system? Part of the answer lies in radioactive decay, the slow breakdown of uranium, thorium, and potassium isotopes trapped in the rocky cores of these worlds since their formation. This heat source is modest but relentless, and in a body insulated by kilometers of ice, it may be sufficient to keep interior temperatures above the melting point of certain ice mixtures for billions of years. Ammonia mixed with water ice, for example, can remain liquid at temperatures far below the normal freezing point of pure water. If these dwarf planets incorporated enough ammonia during formation, pockets of liquid water could persist deep inside them even now. But radioactive decay alone may not explain everything. Tidal heating, the frictional warmth generated by gravitational flexing in bodies with eccentric orbits or large moons, could contribute in some systems. Residual heat from formation, the gravitational energy released when these objects accreted from smaller pieces, may have been retained longer than simple cooling models predict, especially if the insulating ice shells are thicker or more effective than assumed. And the chemistry itself may play a role. Exothermic reactions between water and certain minerals can release heat, potentially sustaining warm conditions in localized zones within the interior long after other heat sources have faded. None of these mechanisms is fully quantified for any individual trans-Neptunian object. The internal structures of Pluto, Eris, Makemake, and their companions remain largely unknown. No spacecraft has orbited any of them. No seismometer has listened to their interiors. No gravity mapping experiment has measured the distribution of mass inside their ice shells. What we have are surface observations, spectroscopic data, and thermal models constrained by physics but limited by ignorance. The interiors of these worlds are among the least explored places in the solar system, and the surprises on their surfaces suggest that what lies beneath may be stranger still. If these worlds are this complex, this active, this chemically dynamic, then the environment they inhabit, the dark, frigid, sunlight-starved space beyond Neptune, demands a second look. The objects are not behaving like passive debris drifting through emptiness. They are behaving like geological systems powered by internal energy sources and shaped by processes we are only beginning to catalogue. The environment they live in was supposed to suppress all of this. It was supposed to be too cold, too dark, too far from any energy source for anything interesting to happen, and yet it is happening. Everywhere we look with sufficient resolution, the frozen worlds of the outer solar system are refusing to be simple. There is a moment during every outbound journey from the Sun when the rules change. It does not happen at a marked boundary. There is no line in space where warmth becomes cold or light becomes dark. The change is gradual, governed by one of the simplest and most merciless laws in physics. The inverse square law states that the intensity of light decreases with the square of the distance from its source. Double your distance from the Sun, and the light reaching you drops to 1/4. Triple the distance, and it drops to 1/9. Move 10 times farther, and it drops to 1/100th. The arithmetic is clean, the consequences are brutal. At Earth's distance, 1 astronomical unit from the sun's solar radiation delivers roughly 1,360 watts of energy per square meter. This is enough to power photosynthesis, warm oceans, drive weather systems, and sustain every living organism on the planet. At Jupiter, 5 astronomical units out, the solar flux drops to about 50 watts per square meter. At Saturn, nearly 10 astronomical units away, it is roughly 15 watts. At Neptune, 30 astronomical units from the Sun, the figure falls to approximately 1.5 watts per square meter. That is less than 1/9% of what Earth receives. The warm, bright, energy-rich environment that makes life possible on our planet has been stripped away almost entirely. But Neptune is only the threshold. Step beyond it into the Kuiper Belt and the numbers become more extreme with every astronomical unit. At 40 astronomical units, roughly Pluto's average distance, solar intensity drops to about 0.85 watts per square meter. Sunlight is now approximately 1,600 times weaker than on Earth. To put that in sensory terms, if you stood on Pluto's surface at local noon and looked toward the Sun, you would see a brilliant point of light, still by far the brightest object in the sky, still bright enough to cast faint shadows, still clearly identifiable as the Sun. But the warmth would be gone. The illumination would resemble something between deep twilight and a brightly moonlit night on Earth. You could read a page by it, but you would feel nothing on your skin. The Sun would be visible and recognizable and utterly powerless to warm you. At 50 astronomical units, where the classical Kuiper Belt was long thought to end, sunlight weakens to about 0.54 watts per square meter, 2,500 times fainter than at Earth. At 64 astronomical units, where New Horizons currently drifts, the intensity is roughly 0.33 watts per square meter. Imagine a single candle burning at the far end of a football stadium. The light reaches you, you can see it, but it does not illuminate anything around you in a useful way. That is an imperfect analogy, but it captures the essential point. Sunlight in the outer Kuiper Belt is present, but it has been reduced to a trace. The temperature consequences follow directly. Without significant solar heating, surface temperatures on trans-Neptunian objects are governed almost entirely by the feeble balance between absorbed sunlight, thermal radiation back into space, and whatever modest internal heat the body generates. For most Kuiper Belt objects, surface temperatures hover between 30 and 50 Kelvin, roughly -220 to -240 degrees Celsius. At these temperatures, nitrogen is a solid that can flow like glacial ice under pressure. Methane is a rigid crystalline material. Carbon monoxide is a hard frost. Water ice has the mechanical properties of bedrock. The chemistry that operates on these surfaces unfolds in a regime so cold that the molecules we associate with gases and liquids on Earth behave like minerals and stone. These conditions do not merely make the outer solar system inhospitable, they make it operationally hostile to every tool humanity has built for exploring space. Consider the problem of power. Every spacecraft needs electricity to run instruments, process data, heat sensitive components, and transmit signals back to Earth. In the inner solar system, solar panels provide that electricity reliably. The Mars rovers, the spacecraft orbiting Venus and Mercury, the probes studying the Sun itself, all of them harvest sunlight and convert it to power. Even at Jupiter, solar power remains marginally viable. The Juno mission orbiting Jupiter carries the largest solar arrays ever deployed on an interplanetary spacecraft, each wing stretching nearly 9 meters long, and they generate enough power to operate the spacecraft at 5 astronomical units from the Sun. Beyond Jupiter, solar power effectively dies. The sunlight is too weak. The panels would need to be implausibly large. Every spacecraft that has ventured into the outer solar system, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, New Horizons, and the Cassini mission to Saturn has relied instead on radioisotope thermoelectric generators, devices that convert heat from the natural radioactive decay of plutonium-238 into electricity. These generators are reliable, long-lived, and completely independent of sunlight. But they are also heavy, expensive to fuel, and limited in output. New Horizons launched with a single radioisotope thermoelectric generator, producing approximately 240 watts of electrical power, less than the output of 3 ordinary household light bulbs. By 2026, radioactive decay has reduced that output to around 190 watts. The spacecraft must operate every instrument, heat every critical component, and transmit data across nearly 10 billion kilometers of space on a power budget that would struggle to run a desktop computer. This power constraint shapes everything about how the outer solar system is explored. Instruments must be designed for extreme efficiency. Data must be compressed and transmitted slowly. Heaters must be rationed. Some instruments must be turned off while others operate, because running them simultaneously would exceed the available power. The New Horizons team has developed updated autonomy software specifically to manage operations at ever greater distances from the Sun, where power continues to decline and communication delays continue to grow. Communication is its own challenge. Radio signals travel at the speed of light, and from 64 astronomical units, that means a one-way signal takes approximately 8 hours and 52 minutes to reach Earth. A round-trip command and response cycle takes nearly 18 hours. Real-time control is impossible. Every action the spacecraft takes must be planned, programmed, and uploaded days or weeks in advance. If something goes wrong, the spacecraft must detect the problem and respond autonomously before ground controllers even know there is an issue. When New Horizons flew past Pluto in 2015, at a distance of roughly 33 astronomical units, the communication delay was about 4.5 hours each way. At its current distance, that delay has nearly doubled, and it will continue growing for as long as the spacecraft operates. The signal strength compounds the difficulty. Radio power diminishes with the square of distance, just like sunlight. At 64 astronomical units, the signal reaching Earth from New Horizons is extraordinarily faint, measured in billionths of a billionth of a watt. Receiving it requires the largest radio dishes on Earth, the 70-meter antennas of NASA's Deep Space Network, pointed precisely at the spacecraft's position, for hours at a time. Data rates are correspondingly slow. Information that a terrestrial internet connection could download in a fraction of a second takes hours to transmit from the outer Kuiper Belt. The entire dataset from the Pluto flyby took over a year to downlink to Earth after the encounter. These engineering constraints mean that the outer solar system is explored not in sweeping surveys, but in narrow, carefully targeted glimpses. We have exactly one spacecraft in the Kuiper Belt. We have flown past exactly 2 trans-Neptunian objects with cameras Pluto and Arrokoth. Everything else we know about the thousands of other objects in this region comes from telescopes on or near Earth, squinting across billions of kilometers of empty space at targets that are small, dark, and slow. And this is where the detection problem becomes acute. Finding trans-Neptunian objects from Earth is one of the most difficult observational challenges in astronomy. These objects are faint, staggeringly faint. A typical Kuiper Belt object a few hundred kilometers across, orbiting at 45 astronomical units, reflecting a small percentage of the already feeble sunlight reaching it, appears at a visual magnitude of 23 to 25. For comparison, the faintest star visible to the unaided human eye is roughly magnitude 6. Each step of 5 magnitudes represents a factor of 100 in brightness. An object at magnitude 25 is approximately 40 million times fainter than the faintest star you can see with your naked eyes on the clearest, darkest night imaginable. Detecting it requires a large telescope with a sensitive digital camera and a long exposure time, typically measured in minutes per image. But faintness is only half the problem. The other half is motion. Trans-Neptunian objects orbit the Sun at distances so vast that their apparent motion across the sky, as seen from Earth, is minuscule. An object at 45 astronomical units typically moves at a rate of about 1 to 3 arcseconds per hour, so slowly that in a single image it looks identical to a background star. To find it, you must take multiple images of the same patch of sky, separated by intervals of hours, then carefully compare the images to identify any point of light that has shifted position slightly. This technique, called shift and stack, or digital tracking, requires sophisticated software that tests thousands of possible motion rates and directions shifting the image frames by different amounts and stacking them to see if a faint source emerges at any particular combination. The computational demands are enormous. A single field of view from a large survey telescope may contain hundreds of thousands of stars and galaxies. Among them, 0 or 1 or possibly 2 moving objects may be Kuiper Belt objects. Sifting the signal from the noise requires processing power, statistical rigor, and carefully designed algorithms that can distinguish genuine slow movers from artifacts, cosmic rays, detector noise, and the countless other sources of false positives that plague deep astronomical imaging. The search for Arrokoth illustrates how excruciating this process can be. After New Horizons flew past Pluto in 2015, the mission team needed a second target, a Kuiper Belt object reachable with the spacecraft's remaining fuel. The problem was that no known object lay within the narrow cone of space New Horizons could steer toward. The team had to find one. They enlisted the Hubble Space Telescope for a dedicated search, pointing its cameras at fields along the spacecraft's projected flight path and looking for the faint, slow-moving signature of an unknown Kuiper Belt object at the right distance, on the right trajectory, within the right angular reach. The search consumed dozens of Hubble orbits, some of the most competitively allocated telescope time on Earth, and sifted through thousands of background sources to identify candidates. The team found several possibilities, but only one, the object that would be named Arrokoth, lay close enough to the spacecraft's path and was bright enough for New Horizons' long-range reconnaissance imager to observe during approach. The margins were razor-thin. If Arrokoth had been a few hundred kilometers farther from the flight path, or slightly fainter, or on a different orbit, the flyby would not have happened. The most detailed observations ever made of a primordial Kuiper Belt object depended on finding a needle in a haystack stretching across the outer solar system, and the needle was found with less than 3 years to spare. This is why the known population of trans-Neptunian objects has grown slowly. Despite decades of surveying, only about 5,000 have been catalogued. Each one represents a significant investment of telescope, time, computational effort, and follow-up observations to confirm the detection and determine an orbit. The objects that have been found are overwhelmingly the brightest and nearest the tip of an iceberg whose full extent remains unknown, and the difficulty increases sharply with distance. An object, at 80 astronomical units, reflecting the same fraction of sunlight, would appear roughly 10 times fainter than an identical object at 45 astronomical units, simply because it receives less sunlight and is farther from Earth's telescopes. This double penalty, less illumination and greater distance, means that the detection horizon for Kuiper Belt objects drops off steeply with distance. Current surveys can reliably detect objects a few hundred kilometers across, at 40 to 50 astronomical units. At 80 or 90 astronomical units, only the very largest objects, those exceeding 1,000 kilometers in diameter, would be bright enough to show up. Anything smaller is invisible. This observational bias is critical for interpreting the apparent outer edge of the Kuiper Belt. The sharp decline in known objects near 50 astronomical units may be genuine. It may reflect a real drop in the number of objects, or it may be an artifact of detection limits. The objects may be there, but they are too faint and too distant for existing surveys to find. Distinguishing between these possibilities requires either much deeper surveys, which the Vera Rubin Observatory's Legacy Survey of Space and Time is designed to provide, or indirect measurements from instruments that do not depend on reflected sunlight. The dust measurements from New Horizons are exactly that kind of indirect evidence, and their implications become clearer when you understand the physics of dust production in the Kuiper Belt. Dust in the outer solar system does not arrive from interstellar space, though a small component of interstellar dust does enter the solar system and contributes to the background. The dominant source of dust in the Kuiper Belt is the Kuiper Belt itself. Collisions between Kuiper Belt objects, even gentle ones, grind material off their surfaces and release microscopic particles into space. Additionally, the steady bombardment of Kuiper Belt object surfaces by high-speed interstellar dust grains acts like a sandblaster, chipping away tiny fragments that become part of the local dust population. Over billions of years, these processes have produced a diffuse cloud of dust pervading the belt, with particle sizes ranging from sub-micrometer grains to fragments a millimeter or more across. Once produced, dust particles do not simply stay where they were created. they are subject to forces that the larger parent bodies can ignore. Solar radiation pressure pushes small grains outward, away from the Sun. The smaller the grain, the stronger the relative effect of radiation pressure compared to the Sun's gravity, and the farther the grain drifts before its orbit decays through other forces. Meanwhile, the Poynting-Robertson effect, a relativistic drag caused by the anisotropic absorption and re-emission of sunlight, slowly spirals grains inward over long timescales. The balance between these forces, combined with gravitational perturbations from Neptune and the other giant planets, determines where the dust ends up and how it is distributed through the outer solar system. Models of this process, calibrated against early student dust counter measurements from New Horizons as it travelled through the inner Kuiper Belt, predicted a straightforward dust profile. Dust density should peak somewhere around the heart of the classical belt, near 40 to 42 astronomical units, where the concentration of parent bodies is highest and collision rates are greatest. Beyond the belt's outer edge, near 50 astronomical units, the parent bodies thin out and dust production drops. Radiation pressure pushes some grains outward, but the models predicted that the dust density should fall off sharply, tracking the decline in the source population. The student dust counter did not cooperate with this prediction. As reported in the Astrophysical Journal, Letters in early 2024, and further analysed through 2025, the instrument recorded dust impact rates between 40 and 55 astronomical units that exceeded model predictions by a factor of 2 to 3. The expected decline near 50 astronomical units did not materialise. Dust kept hitting the detector at elevated rates as the spacecraft pushed deeper into the outer belt and beyond. 3 hypotheses have been proposed to explain the discrepancy, and each one carries different implications for the structure of the outer solar system. The first focuses on the behaviour of the dust grains themselves. Kuiper Belt dust particles are not pure rock. Many of them likely contain volatile ices, water ice, carbon dioxide ice, possibly more exotic frozen compounds. When these icy grains are exposed to solar ultraviolet radiation, a process called photosputtering erodes the volatile component, reducing the grain's mass and size. A smaller, lighter grain responds more strongly to radiation pressure. It gets pushed farther from the Sun before other forces bring it to a halt or destroy it. If photosputtering is more efficient than existing models assume, the dust distribution would be stretched outward, maintaining elevated densities at distances beyond the parent body population. This explanation keeps the source population where it is in the classical belt, but changes how far the dust travels after production. The second hypothesis involves the composition of the grains in a different way. A 2025 study modelled the effects of refractory versus volatile grain compositions on dust transport and found that volatile-rich grains behave measurably differently from rocky grains in their response to radiation forces. The interplay between sublimation, size reduction, and radiation pressure creates a more extended dust distribution than purely refractory models predict. This is essentially a refinement of the first hypothesis, and it can account for some of the observed excess but may not fully explain the magnitude of the discrepancy at the most distant measurements. The third hypothesis is the most consequential. It proposes that the parent body population itself extends beyond 50 astronomical units in numbers sufficient to sustain elevated dust production at those distances. If there are Kuiper Belt objects, even small ones, below the detection threshold of current telescopic surveys, orbiting at 60, 70 or 80 astronomical units, their mutual collisions and their bombardment by interstellar dust would produce a local dust population that the student dust counter would detect as it passed through. This explanation does not require exotic dust physics. It requires more stuff, more objects, more collisions, more source material in a region that was supposed to be largely empty. The 3 explanations are not mutually exclusive. All 3 effects may operate simultaneously, each contributing to the observed excess. But the third explanation, if correct even partially, fundamentally changes the architecture of the outer solar system. It implies that the Kuiper Belt does not end where the object counts drop off. It implies that the apparent edge near 50 astronomical units is an observational artifact, a limit of our telescopes, not a limit of the belt. And it implies that significant populations of icy bodies remain hidden in the darkness, too small and too far for reflected light surveys to detect but numerous enough to sustain a measurable dust environment across tens of additional astronomical units. Understanding the collision environment of the Kuiper Belt adds another layer of evidence. When New Horizons flew past Arrokoth, the near absence of impact craters on its surface carried a powerful message about the small body population in the cold classical belt. Impact craters accumulate over time as objects are struck by smaller impactors. The number and size distribution of craters on a surface tells scientists how many impactors of various sizes exist in the surrounding environment and how long the surface has been exposed. A heavily cratered surface indicates a dense impactor population and a long exposure time. A lightly cratered surface indicates either a sparse impactor population, a young surface that has not yet accumulated many hits, or a process that erases craters after they form. Arrokoth's surface is lightly cratered, and its age is known to be roughly 4.5 billion years. It has been sitting in the cold classical belt since the solar system formed. Crater erasure processes on a body this small, with no atmosphere and no geological activity detected, are minimal. The low crater count therefore points directly at the impactor population. There are far fewer sub-kilometer objects in the cold classical Kuiper Belt than models of collisional grinding predicted. The small body population is depleted relative to extrapolations from the inner solar system's asteroid belt. The cold classical belt has not been ground down by billions of years of mutual collisions into a fine powder of fragments. It has remained remarkably intact, with its original size distribution largely preserved. This finding has implications for the dust measurements as well. If collisions are less frequent in the classical belt than models assumed, then the dust production rate from mutual Kuiper Belt object impacts should be lower than predicted, not higher. Yet the student dust counter measures more dust, not less. This mismatch sharpens the puzzle. Either the dust is being produced more efficiently per collision than models account for, perhaps because icy surfaces fragment differently than rocky ones, or there are additional dust sources beyond the classical belt that are contributing to the observed signal. Interstellar dust bombardment of large surface areas across the belt is one candidate, but models suggest it alone cannot account for the full excess. The most economical explanation remains the presence of unseen parent bodies at greater distances. The collision environment also reveals something about the history of the Kuiper Belt structure. The cold classical belt's gentle, low inclination, low eccentricity orbits and its sparse small body population indicate that this region was never subjected to the kind of violent, dynamical upheaval that would have fragmented its inhabitants and pumped up their orbital velocities. Neptune's outward migration, according to the best models, mostly affected the inner and resonant populations, while leaving the cold classical belt relatively undisturbed. This means the cold classical belt is a sample of conditions in the outer solar nebula roughly 4.5 billion years ago, a region where material accreted into small bodies through gentle gravitational collapse, where collision speeds remained low enough to build contact binaries instead of shattering them, and where the resulting objects have survived essentially unchanged to the present day. This preservation is extraordinary. In the inner solar system, the original planetesimal population has been obliterated. Asteroids have been shattered, reaccumulated, heated, melted, and reprocessed by billions of years of collisions and gravitational perturbations from Jupiter and the other planets. The surfaces of terrestrial planets and moons have been reworked by volcanism, plate tectonics, atmospheric erosion, and impact bombardment. Nearly every record of the solar system's earliest conditions has been overwritten. In the cold classical Kuiper Belt, those records still exist, frozen into the shapes, compositions, and orbits of objects that have barely changed since they formed. Arrokoth is not just a trans-Neptunian object, it is an artifact from the solar system's birth, preserved by the extreme cold, the vast distances, and the gentle dynamical environment of the region it inhabits. But accessing those records is agonizingly difficult, and the obstacles are not only observational, they are logistical, institutional, and material. Even if a new mission to the Kuiper Belt were approved tomorrow, the challenges of actually getting there would test the limits of current capability. The fuel problem alone is sobering. Radioisotope thermoelectric generators require plutonium-238, and the global supply of this isotope is extremely limited. The United States stopped producing it in the late 1980s, and did not restart domestic production until 2015, when Oak Ridge National Laboratory began manufacturing small quantities for NASA. The production rate as of the mid-2020s is roughly 1.5 kilograms per year. New Horizons alone used approximately 11 kilograms. A future Kuiper Belt orbiter, needing more power for a longer mission with higher data demands, might require even more. The supply chain for the single material that makes outer solar system exploration possible is measured in grams per month. Then there is the problem of time. New Horizons reached Pluto in 9.5 years, traveling at one of the fastest launch velocities ever achieved by a spacecraft. A mission to the Kuiper Belt that aimed to orbit a dwarf planet rather than simply fly past it would need to carry enough fuel to decelerate into orbit after a cruise lasting a decade or more. That deceleration fuel adds mass, which requires a larger launch vehicle, which increases cost, which extends development timelines. Mission concepts like Persephone, which proposed orbiting the Pluto system and then exploring additional Kuiper Belt objects, have been studied repeatedly. None has been funded. The practical reality is that no space agency on Earth currently has a Kuiper Belt mission in its funded pipeline. New Horizons is the only spacecraft operating in this region, and no replacement is being built. This means that the window of in situ exploration is finite. New Horizons' power will continue declining. Its instruments will eventually degrade. Its trajectory carries it outward at roughly 14 kilometers per second, and it will leave the Kuiper Belt behind within the coming decades. When it does, the only human-made instrument capable of measuring the dust, plasma, and particle environment of the outer solar system from inside that environment will be gone. Whatever questions remain unanswered at that point will stay unanswered until another spacecraft makes the journey a journey that would take at least a decade, even if it launched in the next few years, which it will not. Every observation of a Kuiper Belt object therefore requires overcoming the same cascading challenges: faint targets, slow motion, enormous distances, weak signals, limited spacecraft power, communication delays measured in hours, a finite fuel supply on the only active probe, and no funded successor. The entire known population of over 5,000 trans-Neptunian objects has been built up over more than 3 decades of painstaking work by survey teams operating the largest telescopes on Earth. 2 objects, exactly 2, have been visited by a spacecraft. The rest are known only as points of light whose brightness, colour and orbital parameters have been measured with varying degrees of precision. For most of them, basic questions remain unanswered. What are their shapes? What ices cover their surfaces? Do they have moons? Are they contact binaries like Arrokoth, or spherical like Pluto, or elongated like Haumea? We do not know. We cannot know from this distance with existing instruments. The physics of the outer solar system does not merely make exploration difficult, it actively resists being known. The darkness, the cold, the distances, and the faintness of the objects conspire to keep this region shrouded. Every fact we have extracted from it has been won against formidable odds, and every new measurement, from the student dust counter's excess dust to the Subaru telescope's candidate distant objects to the James Webb Space Telescope's spectroscopic revelations, has shown that the reality is more complex, more populated, and more scientifically interesting than the models built in the absence of data assumed. The Kuiper Belt operates on timescales that dwarf human experience, and at energy levels so low that they approach the limits of thermodynamics. Orbital periods in the classical belt range from roughly 250 to over 500 years. An object at 50 astronomical units has not completed a single orbit since the United States became a country. An object at 80 astronomical units takes more than 700 years to circle the Sun once. Processes that we would call rapid in geological terms, the convective overturn of Sputnik Planitia every 500,000 years, the glacial flow of nitrogen ice across Pluto's surface at a millimeter per week, are among the fastest phenomena operating in this region. Most changes unfold over millions or billions of years, invisible to any human observing program. Even the light we use to study these objects carries temporal distortion. A photon leaving the surface of a Kuiper Belt object at 50 astronomical units takes nearly 7 hours to reach Earth. By the time we image that object, the information in the light is already 7 hours old. For the fastest moving phenomena, cometary outbursts, Potential cryovolcanic venting this delay is scientifically irrelevant, but for the process of surveying the belt, it means that every observation is a snapshot of a configuration that has already changed, however slightly, by the time the data arrive. The outer solar system does not present itself for observation. It must be dragged into view, one painfully faint exposure at a time. The engineering and observational challenges of this region are not obstacles that will be solved by a single mission or a single telescope. They are structural features of the environment itself. The darkness is not a temporary inconvenience. It is the fundamental condition of the Kuiper Belt. Sunlight will never be strong enough at 50 astronomical units to power solar panels. Radio signals will never travel faster than light. Trans-Neptunian objects will never become bright enough to be surveyed the way asteroids in the inner solar system are surveyed. Every future mission to the Kuiper Belt will face the same constraints that New Horizons faces: limited power, delayed communications, long cruise times, a dwindling supply of the only fuel that works out there, and a target environment so dark and cold that even the most sophisticated instruments must operate at the edge of their capabilities. And yet, every time an instrument has operated at that edge, it has returned data that contradicted expectations. The dust was supposed to thin out. It did not. The surfaces were supposed to be geologically dead. They were not. The impactor population was supposed to follow the same size distribution as the asteroid belt. It did not. The outer boundary of the belt was supposed to be sharp. The evidence increasingly suggests it is not. The physics of the outer solar system tells a consistent story. The environment is real, extreme, and well understood in its broad outlines. The inverse square dimming of sunlight, the thermodynamic inevitability of cryogenic surface temperatures, the engineering consequences for spacecraft design, the observational penalties for ground-based detection, all of these follow from known physics applied to known distances. There are no exotic forces at work. There is no mystery about why the outer solar system is dark and cold. The mystery is about what is in it. And on that question, the data keep outrunning the models. The dust counter measures more dust than it should. The surveys find objects farther out than they expected. The surfaces show activity that the temperatures should forbid. And the instruments capable of resolving these contradictions, Vera Rubin's camera, the James Webb Space Telescope spectrographs, New Horizons particle detectors are only now beginning to deliver the data that will determine whether the Kuiper Belt, as drawn on current maps, represents the actual structure of the outer solar system, or merely the portion of it we happen to be able to see. The most honest thing a scientist can say about the outer solar system is that the map is not finished. This is not a comfortable admission. Humanity has sent 5 spacecraft past the orbit of Neptune. We have telescopes capable of detecting galaxies billions of light years away. We have catalogued over 5,000 trans-Neptunian objects and resolved the surfaces of 2 of them in extraordinary detail. We have measured dust densities in situ, mapped orbital families from the ground, detected atmospheric gases on worlds 45 times farther from the Sun than Earth, and identified chemical signatures pointing to warm interiors beneath ice shells colder than any natural environment on our planet. And yet, after all of that, the basic question of where the solar system's small body frontier ends and what populates it remains scientifically unsettled. The outer solar system is not unknown in the way that distant galaxies are unknown too far for any probe to reach. It is unknown in a more unsettling way. It is right here, within our own planetary system, and we still cannot see most of it. The evidence gathered over the past decade points consistently in one direction: outward. The Kuiper Belt, as described in textbooks for most of the past 30 years, was a region extending from roughly 30 to 50 astronomical units from the Sun, populated primarily by icy bodies in stable or slowly evolving orbits, with a sharp outer edge that marked the transition into effectively empty space. That picture was built from ground-based surveys that could detect objects a few hundred kilometers across at 40 to 50 astronomical units, and from dynamical models calibrated against those detections. It was the best picture available. It is now incomplete. The first cracks appeared with the dust. The Venetia Burney student dust counter aboard New Horizons, measuring interplanetary dust impacts along the spacecraft's trajectory, recorded elevated dust densities well past 50 astronomical units, at levels no existing model of the belt structure could account for. If the Kuiper Belt ended near 50 astronomical units, the dust should have thinned accordingly. It did not. The signal carried a message. Something is generating debris in a region that the standard model said was nearly empty. The second line of evidence came from telescopic surveys. The New Horizons team, working with the Subaru Telescope's Hyper Supreme Cam in Hawaii, conducted deep imaging along the spacecraft's flight path and reported candidate trans-Neptunian objects at distances approaching 90 astronomical units. These detections were published in the Planetary Science Journal in 2024. The word candidate is important. The orbits of these objects are not fully determined. They could belong to the scattered disk, whose members travel on wild, elongated paths that carry them far from the Sun before swinging back. They could be fragments of a more distant population that has never been surveyed, or they could be statistical outliers in the known distribution. Determining which explanation is correct requires years of follow-up observations to track their positions, refine their orbits, and determine whether they represent a genuine population or a handful of exceptional objects. Alan Stern, the principal investigator of the New Horizons mission, described these findings as evidence for a possible second Kuiper Belt, an outer ring of debris beyond the classical belt's accepted boundary. That phrase has generated excitement and controversy in roughly equal measure. A second Kuiper Belt would imply that the original solar nebula extended much farther than current formation models assume, or that some dynamical process transported material outward to populate a region that should have been empty. Either interpretation carries consequences that ripple through planetary science, but the evidence is preliminary. The candidate detections are real, but their interpretation is not settled. Science demands caution here, and the distinction between a confirmed population and a candidate population is not a technicality. It is the difference between rewriting the textbooks and waiting for more data. The broader context makes this uncertainty even more significant. The outer solar system contains several populations of objects that occupy distinct dynamical niches, each one shaped by different histories and governed by different orbital mechanics. The classical Kuiper Belt, the resonant populations locked to Neptune, the scattered disk, these are all relatively well characterized, at least in their broad properties, but beyond them lie objects that do not fit neatly into any established category, and it is these outliers that pose the most challenging questions. Sedna is the most famous example. Discovered in 2003, Sedna occupies an orbit unlike anything else in the known solar system. Its closest approach to the Sun is approximately 76 astronomical units, well beyond Neptune's gravitational reach. Its most distant point is roughly 937 astronomical units. A single orbit takes Sedna over 11,000 years. No known planet or dynamical mechanism in the current solar system can explain how Sedna got onto this orbit. Neptune is too far away to have scattered it there. The giant planet's gravitational influence does not extend to Sedna's perihelion distance. Something else must have placed Sedna on its current path, and identifying that something else has become one of the central problems in outer solar system science. Several explanations have been proposed. A passing star in the solar system's early history could have gravitationally perturbed objects from the outer Kuiper Belt onto Sedna-like orbits. The Sun may have formed in a dense stellar cluster where close encounters with neighbouring stars were common, and those encounters could have sculpted the orbits of distant small bodies before the cluster dispersed. Alternatively, a massive planet, far larger than Earth but smaller than Neptune, could exist in the distant solar system on an orbit that has so far evaded detection. Its gravity would perturb nearby objects, pumping up their perihelia and clustering their orbital orientations. This last idea is the Planet 9 hypothesis, and as of mid-2026, it remains one of the most vigorously debated proposals in planetary science. In 2016, Konstantin Bartygin and Mike Brown published a paper in the Astronomical Journal, arguing that the orbits of several extreme trans-Neptunian objects, those with perihelia beyond roughly 40 astronomical units, and semi-major axes beyond 250 astronomical units, showed a statistically significant clustering in their orbital orientations. They proposed that this clustering could be explained by the gravitational influence of an unseen planet with a mass of roughly 5 to 10 times Earth's mass, orbiting at a semi-major axis of approximately 400 to 800 astronomical units. Such a planet would be extraordinarily faint, reflecting negligible sunlight at that distance, and its orbital period would be measured in tens of thousands of years. It would have avoided detection by every survey conducted to date, not because it does not exist, but because it is too dim and too slow-moving to have been noticed. The hypothesis has accumulated supporting arguments over the past decade. Objects influenced by a distant massive planet should exhibit specific dynamical patterns, and some have been identified in the observed population. Certain classes of trans-Neptunian objects with unusual inclinations and perihelia emerge naturally from simulations that include a Planet 9 mass body. The hypothesis makes predictions that can be tested, which is its scientific strength, but it also faces significant challenges. In June of 2026, a team led by Yukun Huang at the National Astronomical Observatory of Japan announced the characterization of a sednoid object designated 2023 KQ-14. This object's orbit does not align with the orbital clustering predicted by the Planet 9 hypothesis. If the original clustering signal depended on a small sample of objects, and it did, then each new discovery either strengthens or weakens the statistical case. The addition of 2023 KQ-14 weakened it. As Huang stated, the finding lowers the likelihood of the Planet 9 hypothesis, and it raises the possibility that a planet once existed in the outer solar system but was ejected at some point in the past. This does not mean the hypothesis is dead. The sample remains small, only a handful of objects with well-determined orbits. A single non-conforming orbit does not refute the hypothesis, just as a single conforming orbit does not confirm it. The statistical power of the test depends on the total sample size, and that sample is growing slowly because these objects are extraordinarily difficult to find. They are far away, faint, and slow. Each new discovery requires extensive follow-up to confirm the orbit, and the process takes years. The instrument that may resolve this question is already operating. The Vera Rubin Observatory, perched on Cerro Pacon in the Chilean Andes, officially began its legacy survey of space and time in July of 2026. Its 3.2 gigapixel camera will photograph the entire visible southern sky every few nights for a decade, reaching depths no previous ground-based survey has achieved. Within its first years of operation, the observatory is expected to multiply the known trans-Neptunian population by a factor of roughly 10. Among those discoveries will be objects at the extreme outer margins of the solar system, objects on orbits that current surveys have no hope of detecting. If a Planet 9 exists and has sculpted the orbits of distant small bodies into a detectable pattern, Rubin will find enough of those bodies to confirm or refute the signal with statistical confidence. Researchers have estimated a 70 to 80% chance that the observatory will detect such a planet directly within its first few years if it is real. Konstantin Bar-Tigin recently stated that the new batch of discoveries will arrive starting in the summer of 2026, and that it will provide a direct test of all lines of evidence for the existence of Planet 9. If the planet is found, it will be one of the most significant discoveries in solar system science since Neptune itself was identified in 1846. If it is not found, the orbital clustering must be explained by some other mechanism: a passing star, a self-gravitating disk instability, or a process not yet imagined. Either outcome transforms our understanding of the outer solar system, but whether or not a ninth planet exists, the structural complexity of the region beyond Neptune is already confirmed. The scattered disk alone contains a population of objects whose orbits range from near Neptune distances out to hundreds or thousands of astronomical units. These objects are not in stable orbits. They are slowly evolving, being perturbed by Neptune, by galactic tides, and by the cumulative gravitational influence of the Milky Way's mass distribution. Over timescales of billions of years, scattered disk objects can be pushed inward to become centaurs, transitional bodies orbiting between the giant planets, or outward into the most distant reaches of the solar system. Potentially, the Oort cloud itself represents the final and most speculative layer of the solar system's architecture. No Oort cloud object has ever been directly observed in place. Its existence is inferred entirely from the orbits of long-period comets, which arrive from seemingly random directions, with orbital periods of thousands to millions of years. To reach the inner solar system from such vast distances, these comets must originate in a spherical reservoir, extending from perhaps 2,000 to 100,000 astronomical units from the Sun, a shell of trillions of icy bodies loosely bound to the Sun's gravity, slowly being stirred by the tidal forces of the Milky Way and the gravitational perturbations of passing stars. If the Oort cloud exists as currently modelled, it contains more individual objects than the Kuiper Belt by orders of magnitude, but its total mass may be comparable, perhaps a few Earth masses of material spread across a volume of space so enormous that it approaches the distances to nearby stars. The nearest star to the Sun, Proxima Centauri, is approximately 4.2 light-years away, equivalent to roughly 265,000 astronomical units. The outer edge of the hypothesized Oort cloud, at 100,000 astronomical units, extends nearly 40% of the way to the nearest star. At those distances, the Sun's gravity is barely perceptible. Objects in the outer Oort cloud are only tenuously bound, and a slight push from a passing star or a galactic tidal fluctuation can send them tumbling inward toward the Sun, or outward into interstellar space. Between the known Kuiper Belt and the hypothesized Oort cloud lies a vast, almost entirely unmapped region, sometimes called the inner Oort cloud, or the scattered disk's outermost fringe. Sedna and objects like it may inhabit this zone. Its population, its structure, and its relationship to both the Kuiper Belt and the Oort cloud are essentially unknown. The observational tools to survey it do not yet exist in any comprehensive form. It is a gap in the map so large that it dwarfs the mapped portion. This is the reality of the space beyond Neptune. It is not a boundary. It is a transition from the organized, well-lit, gravitationally dominated realm of the giant planets into something fundamentally different. A region where sunlight is a memory, where orbits are measured in centuries and millennia, where objects preserve chemistry from the solar system's first million years, where populations may extend outward in numbers we have not begun to count, and where the basic structural questions — how far does the debris field go? What shaped it? Is anything massive hiding in it — remain open. New Horizons drifts through this transition zone right now. It woke from its longest hibernation on June 23rd of 2026, at a distance of approximately 64 astronomical units from the Sun, roughly 5.9 billion miles from Earth. The radio signal confirming its health took 8 hours and 52 minutes to travel from the spacecraft to the Deep Space Network station near Madrid, Spain, and then to the Mission Operations Center at the Johns Hopkins Applied Physics Laboratory. The spacecraft is operating on updated autonomy software designed for the reduced power and extended communication delays of deep outer solar system operations. Its radioisotope thermoelectric generator produces less power with each passing year. Its instruments are aging. No second spacecraft is on its way to join it, and no funded mission currently exists to send another probe into the Kuiper Belt. Yet New Horizons is still collecting data. Its dust counter continues recording impacts. Its plasma instruments monitor the solar wind at distances where it is thinning toward the boundary with interstellar space. Its ultraviolet spectrograph maps hydrogen gas in the outer heliosphere. During its 321 days of hibernation, the spacecraft gathered and stored measurements that it is now transmitting to Earth at data rates measured in kilobits per second. Every byte of information it sends crosses a gap so wide that the Sun, from New Horizons' vantage point, could be covered by the head of a pin held at arm's length. The mission team had hoped to identify another Kuiper Belt object for New Horizons to fly past, extending the chain of close encounters that began with Pluto and continued with Arrokoth. Searches using the Subaru telescope and the Hubble Space Telescope have not yet found a reachable target. The spacecraft is moving away from the Sun at roughly 14 kilometers per second, and its remaining fuel and maneuvering capability limit the range of objects it could reach. Unless a suitable target is discovered in the near future, a possibility that the Vera Rubin Observatory's deep survey may help realize New Horizons will continue outward without another close encounter, joining Voyager 1, Voyager 2, and the Silent Pioneer probes as one of a handful of human-made objects heading toward interstellar space. But even without another flyby, New Horizons remains invaluable. It is the only instrument conducting in situ measurements of the Kuiper Belt environment. No ground-based telescope can measure dust densities at 64 astronomical units. No orbiting observatory can sample the solar wind at that distance. No Earth-based radar can probe the local particle environment. New Horizons is the only set of hands we have extended into that darkness, and what it feels there more dust than expected. A solar wind thinning toward its terminal boundary, the faint glow of hydrogen in the outer heliosphere is information that exists nowhere else. The picture that emerges from all of this, from the dust counter, from the telescopic surveys, from the spacecraft encounters, from the James Webb spectroscopy, from the dynamical models and the statistical analyses and the candidate detections and the unresolved hypotheses, is not a picture of an edge, it is a picture of a frontier. The solar system does not end at Neptune. It does not end at the Kuiper Belt's classical boundary near 50 astronomical units. It does not end at Sedna's orbit, or at the scattered disk's outermost fringes, or at the inner boundary of the Oort cloud. There is no clean termination point where the sun's influence ceases and interstellar space begins. The transition is gradual, measured in thousands of astronomical units, populated by objects that become progressively harder to detect and progressively less bound to the sun's gravity with every step outward. The familiar solar system, the one with 8 planets, an asteroid belt, and a well-lit stage of gravitationally ordered orbits, is the bright inner chapter of a much larger story. It occupies a tiny fraction of the sun's total gravitational domain. Beyond Neptune, the story continues, but the pages are dim. The objects are there, ancient, cold, dark, slow-moving, difficult to detect, and only partially mapped. Some are small and inert. Some preserve volatile ices that should have been lost billions of years ago. Some show geological histories that the temperatures should have forbidden. Some may belong to populations we have only begun to infer from the faintest statistical signals in the faintest survey data. The outer solar system is like a library, where we have read the titles on the first shelf and opened perhaps 2 of the books. The remaining shelves extend into darkness, and we do not know how many there are. We can see that some of them hold material. We can detect the faint dust that drifts between them. We have theoretical reasons to believe that the collection is enormous, but we have not read it. We have not catalogued it. We have not even confirmed how far the shelves extend. This is what makes the space beyond Neptune worse than the simple phrase suggests. It is not worse because it is hostile, though it is colder and darker than any environment humans have experienced directly. It is not worse because it is dangerous, though spacecraft operating there function at the limits of their engineering. It is worse because it is unsettled. The scientific picture is incomplete in ways that matter, not just for understanding the outer solar system as an isolated region, but for understanding the solar system as a whole. The Kuiper Belt structure encodes the history of planetary migration. The scattered disk's population constrains models of how Neptune interacted with the primordial debris field. The presence or absence of a distant massive planet reshapes the dynamical architecture of the entire system. The Oort cloud's existence and properties determine the origin of long-period comets that occasionally plunge toward the inner planets. The volatile chemistry on distant dwarf planets informs our understanding of where water and organic molecules were available in the early solar system. These are not obscure academic questions. They are foundational questions about how our planetary system was built and how it works, and the answers lie in a region so dark, so cold, and so far away that extracting them requires the most powerful telescopes, the most patient surveys, and the most distant spacecraft humanity has ever deployed. Neptune was never the edge. It was the last place we recognized. Beyond it, the solar system does not end. It transforms. The orbits grow longer, the objects grow fainter, the sunlight thins to a whisper. The temperature drops to within a few tens of degrees of absolute zero. The distances stretch until communication with Earth takes the better part of a day. And still, in that thinning, freezing, darkening space, objects orbit, dust drifts. Chemistry operates, surfaces evolve, structures persist that we have not yet mapped and may not fully map within our lifetimes. The sun is still visible from 64 astronomical units. It is a sharp, brilliant point brighter than any star, still unmistakably the center of the system that bears its name. But it no longer warms anything. It no longer powers anything. It no longer dominates the sky with the authority it carries from Earth. From out there, the sun is a beacon marking the direction of home. but it is not home. Home is 5.9 billion miles behind. Ahead, there is only more darkness, more cold, and more unanswered questions receding outward into a frontier that humanity has barely begun to explore. New Horizons drifts on, the only active witness, carrying instruments built by human hands into a silence so vast that even light takes hours to cross it. Behind the spacecraft, the sun shrinks. Ahead of it, the Kuiper Belt continues or ends or transforms into something else. We do not yet know which, and that uncertainty, that unfinished map, that yawning gap between what we can see and what we suspect is there, is the truest measure of the space beyond Neptune. It is not empty. That is the problem. It is not empty enough for comfort, not mapped enough for confidence, not understood enough for closure. It is a region where the solar system's bright, ordered architecture gives way to something older, colder, and less certain, a frozen archive of 4.5 billion years of planetary history, scattered across distances that resist every attempt to survey them completely. The space beyond Neptune is not where the story ends. It is where the story becomes too dark to read, and we are still learning how to bring the light.